Hi, what are you doing with the board? I'm about to derive an equation for the catenary curve for all hanging chains. Oh, is that the same curve that minimizes potential energy and appears all the way throughout nature and engineering? Yeah, that one. Okay, I'm gonna solve this one. We start off with a small part of the chain, which I'm going to just call dm. Now, what forces are acting on this? First of all, we have the tension force, which will be acting along the string, and this means that we're going to have a tension vector that is acting along here. I'm gonna call that t at some coordinate x, and then a little bit further to the right we're going to have another vector which is going to be acting this way, and the tension might be a little bit different, so I'm going to call that t of x plus dx, where dx is essentially just this distance across here. Now it's time to split those two vectors into vertical and horizontal components and then see if we can do some tricky balancing. So this one across here is going to have a vertical component. I'm going to call that ty of x, and we'll also have a horizontal component. Let's call that tx. Similarly to this one, is going to have a component to the side. Let's call that tx again, and a vertical component which will be acting upwards, and this here is going to be ty, but now this will be evaluated at x plus dx. Now notice that I just called these components with the same symbol. The reason for that is that those are the only horizontal forces that are acting on this segment. And because the chain is stationary in the horizontal direction, it is not moving anywhere, those two components will have to be the same, i.e. t of x at position x will have to be the same as t of x at position x plus dx. In other words, we can say that the horizontal tension is a constant. I prefer just calling this c, so I'm going to magically change this to c. Ta-da! Now the y direction is just a little bit more interesting. The reason for that is because we have one more force that we've not mentioned just yet, and that of course is the weight. So we're going to have an additional vector acting down here, which will be the vector of the weight, and we can sum in all the forces in the y direction which have to balance out in either direction if this mass is to remain stationary. So we can say that t of y at x plus dx, and let's take away the other component t of y at x because it's acting downwards. Take away t of y at x, and this better be equal to the force of the weight, which is just mg, and our mass in this case is not going to be m because we're dealing with a small mass. This will be dm multiplied by the gravitational acceleration g. And now let's do some mathematical trickery. So let's consider the mass per unit length, which is m, which is the mass of the entire chain, divided by L, which is just its length. Well, can we express the mass dm in terms of its length? Now, given that's essentially an arc, I'm going to call essentially the arc length from here to here, let's call that ds. Well, if we think about it, if we apply this to dm, this will have to be equal to the total mass multiplied by the proportion of its length divided by the total length. For instance, if the total length was, let's say, 10 meters and this segment here was just 1 meter, then its mass will be 1/10 of that, but that here is assuming uniform mass distribution. Okay, my second bit of mathematical trickery would be to express this ds coordinate in terms of the geometry of the situation, in terms of dy and dx. So we already know that the length of this small segment is dx. Let's also say that the height is going to be dy. In the limit that this triangle is really small, I can directly apply Pythagoras' theorem, and I can say that ds will be the square root of dx squared plus dy squared. Now let's just take dx outside of the square root sign. So what are we going to get? Dx, the square root of 1 plus dy squared over dx squared. I can already sense that this thing will end up leading to an interesting differential equation. And now what I'm going to do is bring those two definitions into the equation that I have here. So rather than dm, I am just going to write m times ds, divide that by L, and we had a factor of g, which we shouldn't forget. And rather than ds, I'm going to write, maybe I should just write that over here on the side, dx times the square root of 1 plus the dy squared by dx squared. Wait, hang on a minute, just focus on the left-hand side of this equation. Does that look suspiciously similar to something that you might have seen at the very beginning of your calculus class? Oh wait, of course, it's very similar to the fundamental definition of a derivative. So, tell you what, we've got a factor of dx here. Let's bring that over on this side. So I'm going to get rid of this dx. I'm going to put that in here, and I will definitely have the very definition of the x derivative of the ty component, i.e. the left hand side is just dty by dx, and this is equal to mg divided by L times the square root of 1 plus dy squared by dx squared. Okay, well, on the left hand side we have the x derivative of ty. How would ty depend on x? We can once again just use kind of simple geometry here and realize that ty over tx geometrically will have to be similar to dy divided by dx. So this means that ty will be dy by dx multiplied by tx. However, remember that tx was indeed a constant, so this here means that ty will be dy by dx multiplied by a constant. Now what I'm going to do is I'm going to take this, I'm going to sub that into this equation across here, and then I'm just going to differentiate. So what is the x derivative of ty? Well, this here will just be the second derivative of y with respect to x, so we can just write over here d squared by dx squared. Then we have a constant which is c, and this thing together will be equal to mg over L. I'm going to bring this constant over on this side of the equation, and then I have the square root of 1 plus dy by dx, and all of this is squared. Now mg divided by lc, I'm going to be using that quite a lot when I'm solving this equation, so I'm just going to say that mg divided by lc, let's just call that gamma, one of my favorite letters. Let's make some space to actually solve this. So how do we approach such an equation? First of all, we can make our lives easier because we can see that we have this repeating factor here. So we can just say that dy by dx itself is just equal to some new constant. Let's just call that z. Okay, well, that means that this here is just dz by dx will just be given by gamma times the square root of 1 plus z squared. This is probably a separable differential equation, so let's bring all the z terms onto one side. Typical for z physics, that will just equal to gamma dx. And now what I'm simply going to do is just integrate both sides with each respective variables. We integrate this with respect to z. I'm going to integrate this with respect to x. Okay, well, this here is very similar to a trig integral, and it reminds me of the famous trig identity. It's not quite there yet, because what we really want is the square root of 1 take away a quantity squared in order to really do this integral. So we're going to have to introduce yet another substitution. So we can say, I'm going to write this up here, that z will be I multiplied by yet another variable w, where I is just the imaginary number. Okay, well, with this in mind, the integral on the left-hand side can be expressed far more easily. So first of all, dz will just be I dw, and then shall we just write down the whole integral? So this will turn into the integral of I dw, and then that will be divided by the square root of 1 plus, now z squared is I w squared, so the square of I is just minus 1, so this will turn this into the integral that we want, because this here is actually the integral of dw divided by the square root of 1 take away w squared. And now we're ready to apply our trigonometric trick. So shall we just say that w is sine theta? This of course means that dw, what is that going to be? So this here will be cos theta, then we need to differentiate d theta. Okay, so this here will turn this integral into I, then the integral of cos theta d theta, divide that by the square root of 1 minus w squared, i.e. the square root of 1 minus sine squared, which is just cos theta. So this integral right here will just be the integral of 1 with respect to theta, which is just I theta plus some constant of integration I'm going to add in a minute. Okay, well, this here though is the integral in terms of theta. How is theta related to w and then later on to z? We know that w is sine theta. This of course means that theta will be the inverse sine of w. In other words, this integral here should be equal to I times sine of w. Well, w is going to be z over I, so I'm going to write this as z over I. So many substitutions in this derivation, it's absolutely brilliant. And now we're ready to plug this integral right here. Let's see what we're going to get. I sine inverse sine of z divided by I will just be equal to the integral of gamma dx, which is just going to be gamma x plus some sort of a constant of integration. Okay, well, let's bring the I on this side here, and let's also take the sine of both sides. So what we're going to get is z will be given by I multiplied by the sine of gamma x plus a divided by I. Z though is just given by dy by dx. So we can say that dy by dx will be given by I sine. Now dividing by I is the same as multiplying by minus I, because 1 over I is equal to minus I, gamma x plus a. And this right here is actually the very trigonometric definition of the hyperbolic sine function. So we can directly say right here that dy by dx will just be given by the hyperbolic sine of gamma x plus a. Now we have a differential equation in terms of the hyperbolic sine. So dy by dx is just that. How do we find y? Well, we're going to need to integrate the hyperbolic sine function. The easiest way to integrate the hyperbolic sine is in terms of its fundamental definition in terms of exponential functions. So we can just say that, let's see, dy by dx. Now sine, following the fundamental definition, which I'm going to leave this right over here, will just be given by e to the theta, which is gamma x plus a, take away e to the minus theta, which is e to the minus gamma x, take away a. Then we're going to be dividing that by 2. Now we're ready to integrate this with respect to x, and it's actually quite an easy integral. So what are we going to get? Integrating this is not so bad. We're going to get a factor of 1 over gamma e to the gamma x plus a, and then take away, we have a factor of minus 1 over gamma, which will turn this into a plus 1 over gamma e to the minus gamma x, take away a, divided by 2. Okay, I'm going to factor out the 1 over gamma. I'm going to leave that up here because this expression here is actually the very fundamental definition of the hyperbolic cosine function. And some constant of integration. Don't worry, I've not forgotten. And we can actually express the shape of this very curve as 1 over gamma cosh of gamma x plus a plus another constant, which denotes the initial conditions of this problem. Now, this problem actually reminds me of one of the most beautiful differential equations and probably the most important equation in physics and applied mathematics, and that is, of course, the wave equation. And if you want to see the wave equation in action, you absolutely cannot miss this video right over there.